So today we are going to look at number systems and conversions. So whatever I've provided is just a summary, a guide to help you understand. So I'd want you to go through the notes. The notes are a bit comprehensive. Go through the link that I've provided, and also go through the video. The video is also very comprehensive. So this is just to help you get some foundations to understand about the number systems. And now regarding the number systems, there is the common number systems that you have been using, and I hope my screen is visible even to your head. Mostly been used to the decimal number systems. So for those of us who did maybe computer studies in high school, you are likely to be conversant with what is on your screen right now, but if not, this is the time to know what exactly this is. Now, we have the decimal number system. This is what we've been using all through. So don't have like to go explaining to details. We've been using this all the time. It is the most and widely used system. So you can see that is usually to base 10. Base 10 usually start counting from 0, 1 up to 9. So if you count all these digits, there are 10 of them, and that's what we call it as, or rather we have it as base 10. So these are the normal calculations you do. 2 plus 2 is equals to 4. 10 plus 10, whichever the basic mathematics you know. So from your class, I don't know whether pre-unit or whatever, this is what you started, you were taught the moment you joined that class. So we're still going on with it. Then we have another number system we call the binary system, the octal system, and hexadecimal system. So the binary system is usually of base 2. We only have 2 digits, and 2 digits I mean only zeros and 1. So mostly these are just like electronic pulses. So it's like you switch on the light and off. So the light can either be on or off. There is no other state. So in the binary system, that's what the machines understand. So each digit here is what you call a bit. So this is a bit. One is also a bit. So a group of these bits, 8 of them make 1 byte. And I think this was provided in the memory. So the last section under the topic, computer memory. So 4 of these bits, that's what we call a nibble. And a group of these 8 of them, either zeros or ones or a mix of zeros and ones, 8 of them is what we call a byte, right? So remember now, everything is based on that. And that's why sometimes you come and find out that you are saying that you have a memory of, maybe your phone has a memory of 4 GB, 8 GB, 16, 32. So how do we arrive to this? If you convert the 4, 8, 16, 32, 64, they are all powers of 2, right? Because that's what the machines understands. So we work with these bits or these digits. So that's why you will never find that you have a RAM of 5 GB. You can barely find that. So it's either you have 2 GB or 4 or 8 or any powers of 2, right? So that's where this comes from. Now, the octal system, which is base 8, it has 8 digits. So its base is 8. So starting from 0 to 7. So if you count these ones, these are supposed to be 8 digits. So each digit, again, in the octal, represents a specific power of 8. So here we say this is a power of 2. This is a power of a base of 8. A specific power, but its base must be 8. A specific power, but its base must be 2. So 2 to power 0, 2 to power 1 in that order. Here 8 to power 0, 8 to power 1, 8 to power 2 in that order. So there are only 8 bits. There are only 8 digits, that is. So 3 bits of this binary number system. So we are going to look at the conversions for the same. So when you come to the hexadecimal number system, the hexadecimal number system, I think those of you who have not forgotten their high school, I don't know whether Form 2, a hex here, we have like combination of 2, a hex and a decimal. The decimal we know already is 10, so we have 10 digits in decimal. Hex here is 6, right? So those polynomials, even from the polynomials, you're starting from the triangle, the hexagon, those octagons, nonagons, those figures with many sides. So again, the hex starts for 6. So if you take 6 and 10, that becomes what? 16. So that's why you have a base of 16. Again, something you have to note in the hexadecimal number system. Now it has 16 digits starting from 0. But note that the moment we get to 9, we don't go to 10, right? So we go to A. So it's like just you have, instead of writing 10, 11, 12, 13, 14, 15, you're supposed to substitute from 10 to 15 with the letters here, right? So we are going to see how we are going to maybe do the conversions of mostly the hexadecimal number system. So you have seen that the range of the hexadecimal is 0 to 9. Then after 9, we move from A to F. So a base of 16. So 16 to any other power. So the position of each digit in a hexadecimal number system represents a specific power of base 16, as long as you have 16 to power something. So to power 0, to power 1, up to whichever power. So that is what you call the hexadecimal number systems. And these are the number systems you're going to look at in this topic. So in the video, there is an additional number system of BCD. So I want to leave that one to you so that you create some time and go and look at it. Now, next, we're going to look at, I think I've already explained this a bit. So the table here shows the 4 number systems: the decimal, binary, octal, and hexadecimal. So the decimal obviously starts from 0 to 9. Binary are only 2, 0 and 1. So you can have a variation of all those numbers. Any other number can be presented in binary. Octal, you said it's from 0 to 8, but now any other number as long as it's base 8, right? So hexadecimal, as you have explained. So these two tables, the table in the next slide is just a continuation of the previous slide. So we are going to look at, most importantly, about now the conversions. So from the illustration or from the diagram on your screen, you see we have the 4 number systems: the decimal to base 10, octal always to base 8, binary is always to base 2, and hexadecimal. So the arrows indicate the conversion. For instance, the decimal, we can convert to and from the binary number system. The decimal again can be converted to and from octal number system, decimal again to and from the hexadecimal number system. So we are going to look at each conversion at a time. So decimal to any of the 3, octal to any of the 3, binary to any of the 3, and hexadecimal to any of the 3. And here below are examples. So mostly, because we've just been using to the decimal number system, we barely write the bases. But ideally, we are supposed to be writing the base. So 25, if it is a decimal, you're supposed to have a subscript of 10. So ones and zeros here, these are binary. Of course, it's always to base 2. 31. So for us to differentiate between 31 and 25, so how do we know whether that one is an octal? How do we know this is a decimal? So we differentiate that one by the base. So this is the base here. Then we have the hexadecimal number system. So we can have 19A, 19A, B, C, 19 up to F. So the moment you put it to base 16 again, you are going to know that that is a hexadecimal number system. That is very important. Now I want us to start by trying to convert to the binary number system. So the examples here, we start from binary to decimal, then we move from binary to octal, then binary to hexadecimal, as per our initial diagram that in the previous slide. So how do we change a binary number? How do we change a binary? Let's maybe, for example, say you have a number like 1011. So how do we convert this number here into a decimal? Because we might hardly understand what this one is, though the machines understand because they work in the binary number system. How do we understand, or how do we convert from this one to this? So that is what we are going to do. And this is just an illustration, and make sure you do practice. So in binary to decimal number systems, there is just mostly we are going to find a common technique. So the technique used to convert from binary to decimal is almost similar to what you use from binary to octal and binary to hexadecimal. Because if you are converting to decimal, let's go through the example maybe so that you understand what you're saying. So the technique here, we multiply each bit by 2 to the power n. We are going to see what exactly n is. And because this is binary, that's why we are saying 2. So it is to base 2. 2 to the power, anything must be to base 2 to the power something. So the weight in the position of bit starting from 0 on the right. Then after that you add. Let's look at that example here. So we have a binary number here, 101011 to base 2 to indicate that this is a binary number. So we want to convert this number to decimal. So how do we do that? One of the simplest ways is to put your numbers as I've indicated in this table. So you put these binary numbers, binary bits, so 10111, then starting from right to left, you put 2 to power 0. We must always start from power 0. Then 2 to power 1, 2 to power 2, 2 to power 3, in that order up to the point where all these numbers, you exhaust the numbers that you're given. After that, you're supposed to take these two and multiply. So 1 times 2 to power 0, 1 times 2 to power 1, 1 times 2 to power 2, in that order up until the last. So the moment you multiply these numbers, like the case here, so make sure you multiply all of them, then you add the results of what you get, right? So I hope you understand that. So maybe we should have included another row here to include maybe the product of these two. But anyway, this one is here. So if you take 1 times 2 to the power 0, which is this one, any number raised to the power 0 is always what? 1. So irrespective, 1 million to the power 0, that is 1. 2 or 30 to the power 0 is always 1. So this is just like 1 times 1, we get 1. We go to the second one, 2 to the power 1 times 1, which is here, we get 2. 2 to the power 2 times 0, any number multiplied by 0 is a 0, of course, which is here. Then 2 to the power 3 times 1. So the 2 to the power 3 is 8 times 1. 8 times 1 is 8. 2 to the power 4 times 0 is 0. 2 to the power 5, that is 32. Then make sure you add all these resulting multiplications here. So the moment you add, you're going to get that 2, this is 40, 42, 43. So 43 to base 10. So that is how you convert any number, any binary number to
Excuse?
yes.
Excuse?
Yes.
Why is 43 to base 10 and not to base 2?
Very good question. He's asking, why is 43 to base 10 and not to base 2? So can we have somebody maybe trying explaining to, what was the name of the person who was asking the question? I didn't check.
I'm Felix Mutwa.
Felix. Felix has a question. So you can either choose to unmute yourself or type in the public chat.
Because you have changed the binary, you are changing from binary to decimal.
Yes, because we are converting from binary
Decimals.
to what?
Decimals.
To the decimal. So 43 is the decimal equivalent of this binary number. And all the binary number must be to power 2. So once you convert this binary number to a decimal, we can no longer use base 2 because we already done the conversion, right? So I hope that question is clear. So we are converting from binary, and that's what he said. We are going to start with converting the binary here to decimal, right? So we had an example of a binary number. We have converted to decimal number system. Maybe I may choose to show you another method here. There's what you call, there are several methods, of course, of doing this. This is one of the most commonly used methods. But then those who are going to pursue maybe IT in IP addressing, there's what you call the magic numbers. Now, what are magic numbers? Let me just maybe illustrate here. So you have 1, 2. So every time we come to this side, the number doubles. So 1 double is 2, 2 double is 4. Then we go to 4 double is 8. Then after 8, we go to what? 16. So we double, we go each time we double. That's 2, then 64, right? Let's say, for instance, we want to convert 43 back to binary. So this one again from here comes to 64. This is 128. So each moment you step, because we are moving from right to left, the number doubles. So let's see what is 43. Maybe let's assume we want to convert 43 to this one. And remember, each value here represents a bit, right? So this is a bit, 1 bit, 1 bit, 1 bit, up to whatever. You can go up to 16 million. So let's try maybe converting. How do we convert 43 back to binary using the magic number here? So this is what you do. Look at 43. What are you likely to get? Which values can add to 43? Which values? So we usually first look at which is the biggest value that is, if not 43, if you cannot get 43 from these numbers, then which is the closest? And we see that the closest is what? 32. So we pick 32 there. Remember that 2, we said that's a bit, right? Then that the remaining numbers from 43, so if you take 43 minus 32, that is what? 11, right? So we have already, and you have a question you can always ask. So we have already found out that we have within the list here, the number closest to 43 is 32, right? So take note of that 2 there. Then the remaining number after you have picked 32 is 11. So again, we go back here, which is the closest number to 11. And you find that you can only go as close as 8, right? So that is another bit. So now 11 minus 8, that is what? Now 3, right? So which is the closest number in our list that we can get to 3? Of course, 4 is bigger than 3. So you're only left with 2 and 1, because 2 and 1 is what? 3. In fact, it's just like you're looking, I don't know whether you call them multiples. I don't know for addition what you call them, but in multiplication is like what you call the multiples. Let's say 25 in multiplication is equivalent to, maybe you can say 5 times 5. But in this case, because you are adding, so 43 is equivalent to, using this number as they should be, there are here, 43 is equivalent to that 2 plus 8, which is 40, plus 2, which is 42, then plus 1, which is 43. So this is a bit, this is 1 bit. The number that you have not used, you usually put as 0, right? The number that you have not used. So we finally end up with 101011, which is the same as 101011. I hope that is clear. So you can always use what you call the magic numbers. You can also use what we call the magic numbers here. It's usually the easiest way, because you simply go and select. You want, let's say again, let's take another example. Let's take like 28. So 28 to base 10, we want to convert that one to binary. So how do we do that? Come here. We see that the number nearest to 28 is 16 here. So we pick 16. So 16, if you take 16, the remaining number, you take 28 minus 16, you'll be left with 12. So again, this is 1 bit. So 12, what can equate to 12 in all this? So we see that 8 plus 4 is equals to 12. So you can pick now 8 and 4. So this is 1 bit, then the remaining we shall zeros. The preceding zeros don't have the effect. So here you can put as many zeros as you want. So if you were to convert 28 back to binary, then it would be just 1, 1, then 1, 0, 0. And maybe you can try your own time and convert and confirm that. So This is simply how we convert these numbers to what? That is how we convert now binary to decimal. It is very simple. Then we have seen the way back. Now let's go to the next conversion, which is from octal to decimal. I thought we should have had, let me check on that. Well, let's convert. We have seen how we move from binary to decimal and back. Let's see how we can move from octal to decimal. So we are basing on the decimal. This to decimal, this one to decimal, this one to decimal. We are starting with that. So how do we convert now an octal? Remember here, there's one thing you're going to find in common. Maybe I'll explain after the conversion. So Nyambu, I don't know whether this Nyambu is your Nyambura or Nyambu. You're asking, are those magic numbers taken randomly, or where do you get them from? These magic numbers, they're not just random numbers, but the thing is you start with 1. And each time you double this number as we move to the left. So you have 1. As long as you start with 1, you come to 2. Each time this number doubles. So double, you get 4. Each time you move to the next step, you double, this is 8. This time you come this side, this is 10. And sorry, this is 16. And they proceed up to, you can go up to whichever millions you want. So that is how we take those ones. We get, that's why we get the numbers. Then what about the wrong division method? We are going to get to there. We will get there. So don't mind. Now let's see how we convert octal. We have moved from here to here. This is the order in which we are moving. So now we are in octal.
Excuse me.
Yes.
How can we convert a binary number with a decimal point to a decimal form?
Good. There's an example, and I will show you that, right? So he's asking, how do we convert a binary number with a decimal? So on the slide, there is an example. I'm going to demonstrate that. So this is what you have started. This is what you are going to go to next. Then eventually you go to this. At least we see how we can convert all the other number systems to binary. Let's look at the technicality of the example of that. So if you want to convert from octal to decimal, the technique is simple. So multiply each bit by 8. So remember, for 8 to power something. Remember, for decimal, we were using, from binary to decimal, we were using base 2. Base 2 to power a certain number. Now we move to 8. And maybe if I move a little bit ahead, when you go to hexadecimal, all our numbers will be to be 16. So 16 to power something, 8 to power something for octal, 2 to power something for binary to decimal. So that's how we're going to look at it. Then the other workings are the same. After you multiply, add the results. Let's see that with an example. So we have an example here. 724 is to base 8. That simply tells us that this number is an octal number system, right? So how do we do that? Again, you create a table with the number 7 to 4. They're coming from here, those 3 numbers. Then below each, you always start from left, from right to left. Actually, now because you're converting from octal to decimal, octal is 8. So you just simply put 8 to power 0, 8 to power 1, 8 to power 2, and you can proceed as long as this number is available. So what do? You repeat the same thing like you've done in binary. Take these two numbers, multiply them. Take these 2, multiply. Take these 2, multiply. So any number is to power 0. So this multiplication is what you have here. 4 times 8 to power 0. Of course, any number is to power 0 is 1. So we get 4. 8 to power 1 times 2, 16. 8 to power 2, this is 4 times 7, which is 448. And then you add. So this is addition here. So you add these 3 numbers. And eventually you get what? 468 to base 10. Right? So I hope that one is clear. So Anwar Geshi, is it a must you start with the one that is the magic numbers? Yes, you must start with 1. It always starts with 1 for the magic numbers. So start with 1 and make sure you double each time you move from right to left. So it is as simple as that, converting from, now this is octal number system to decimal. Now let's look at the final one. We have looked at this, and I'd like you to note the simple thread that we are creating. So here we took the number with 2 to the power something, a certain number. So we multiply the other numbers. Here, because it is octal is 8, you simply take this 8 to the power a certain number, then multiply. So here this can also tell you, because hexadecimal is 16, even before going to the example, we automatically know that this will be 16 to the power a certain number, right? Now, Adrian, you're asking whether it's a must to draw the table. It's not a must. It's not a must. The table is just simple to guide you. If you choose to use the table, well and good. If you choose to just multiply direct, well and good. If you choose to use the magic numbers, well and good. As long as you understand, right? So let's go to how do we convert a hexadecimal number to decimal. In hexadecimal number system, the technique is almost the same. It's only that we are changing what? The multiplier here. So we'll be multiplying by 16. Remember the previous number we multiplied, we had 8 to the power something. The first one, it was 2 to the power something. So this is binary, octal, and hexadecimal. So the trade is the same. It's easier to understand. Let's see with an example here. So we have a number here, A, B, C to the power 16, and you're required to convert that to what? To decimal. So you're going to note that, remember we said that the moment hexadecimal moves from 0 to 9, and instead of going to 10, we go to A. So we have A, then B, C, D, E, and F. So A is equivalent of 10, right? But in hexadecimal, you don't write 10. B is equivalent to 11, C is equivalent to 12, and you go that way up to 15, right? So let's see. So how do we convert that? This is A, B, C, right? You raise the number, create this table, it's simpler. You may choose to or not. So then we always start with, now this is hexadecimal, which is 16. We always start from power 0. So we move 16 to power 1, 16 to power 2. The moment you are in, now you multiply these two numbers. You multiply, and after multiplying, you are supposed to add them, right? So 16 to the power 0 times C. So what exactly is C? You come and see that C is what? 12. And that's why you have 12 here times 16 to the power 0, which is 1. Then 16 here, B times 16 to the power 1. B times 16 to the power 1. But what is B? You see B is what? 11 from here. Then again, we have A to the power 16. 16 to the power 2 times A. But what is A? A is what? 10. So 10 times 16 to the power 2, which is 256, and you get these 3. Then when you get the results, you add them. So the moment you add, the resulting number will now be an equivalent of to base. You already have converted this one to decimal, and that is as simple as that. So I think put a summary here of the 3 number systems. So this is, we are converting from the other number systems to decimal. So this is binary, this one is octal, and this one is hexadecimal system. So we are following the same trend. Binary base 2, multiply across. Octal base 8, starting with power 0, multiply across. 16 from power 0, multiply across. So we are simply following the same trend, and it is easier to understand. So as long as you take these numbers and add them. So multiply, when you multiply them, add the result to this, right? The same case follows here. So you go multiplying up to this one, and you continue adding the results. So you see there is a common thread when you're converting to decimal. So you don't have like to go cramming and all those things, no. So the moment you note the thread, as long as you know from which number system to which one. So it's very simple. Hassan, you're saying that you have a question here. So how are we adding those and that power 10? I don't exactly understand your question. So if you, I would suggest you unmute. I would suggest you unmute. Maybe you use your mic and seek more clarification. So the result we are going to get from here, we are converting from all these now finally to decimal. So the number you are going to get here, maybe let's say 10, it will be to power a base 10. So initially it was base 2, a binary number, base 10, base 8, base 10, base 16, base 10. So that's it. So let's go to the other conversion. We have seen how we convert these three numbers to decimal. Now let's see, now we have done with decimal, conversion to decimal. Then let's see how we convert all these other numbers to binary. How do we convert decimal to binary? Octal to binary, and eventually hexadecimal to binary. So how do we do that? So Diembo is asking where the base 10 is coming from. So the base 10 is coming from, remember before this, we were converting all these numbers to decimal, binary to decimal, this to decimal, and this to decimal. And we see that all the decimal number system is usually to base 10. So where is the 10 coming from? Remember, we usually count from 0 up to 0, 1, 2, 3, 4, up to 9. So if you count these numbers, 0, 1, 2, 3, 4, you count them, literally counting, you're going to get 10 digits. And that's where base 10 comes from. So you have 10 digits. Binary is to base 2. Where do we get these 2 digits? Because it's only 0 and 1. That's why it is always to base 2. Octal, we see it's base 8. You always count from 0 up to 7. So if you count 0, 1, 2 up to 7, the total you get 8. Hexadecimal, they are 16, right? The hex and decimal. Decimal is 10, hex is 6. So those are 16. So we count from 0 to 9. Then after 9, you don't go to 10. You go from A to F. And so if you count all these ones, they are going to give you what? 16. That is where 10 is coming from. Now we have come to now the conversion of decimal to binary. So we want to convert this to binary, octal to binary, and hexadecimal to binary. You're going to find that it's likely the technique will be the same. So Wakenya is asking, so when we start the binary one, the base is 2, but at the end the sum is 10. So remember, we were converting from binary to decimal. So we were moving from base 2 to base 10, right? You have to understand that. You move from base 16 to base 10, base 8 to base 10. I hope I've answered you, Kenya. Let's see the example of decimal to binary. There is an example here. So there was that person who asked about the decimal, how do we convert a decimal number? So we shall see that. There's also somebody who was asking the wrong division. So there are two ways we can convert a decimal number to a binary. Remember, a decimal number could either be a whole number or a decimal number. So here, for instance, we have 43 to base 10. This is a decimal. So we want to convert this to binary. How do we do that? Or you're presented with a case where you have a decimal number. So a number that is having a decimal, we convert on to what? To binary equivalent of decimal equivalent. So how do we do this? I think somebody has listed where the wrong division comes in. Now the division comes in here. How do you convert now 43 to binary? This is how you do it. Wrong division. This is class 2 work. Nani ya kufika class 2 hapa? I want to believe that who could skip class 2 or 3 there, or grade 2, whichever you went through. So you take the number here 43 and you go dividing by 2 until the remainder is what? We have no more division going on. So let me just explain this example here. So we have 43 divided by 2, that is 21. remainder 1, because 21 times 2 is 42, 42 plus 1, 43. So always take note of the remainder. 21, again, you divide by 2. That is 10, because of 20 remainder 1. In class 2 work, I don't know why I should be explaining so much. I hope it is clear to you guys. But the thing I would want you to note is the remainder. Let's go. 10 you divide by 2, that is 5, with no remainder, remainder 0. So again, we have now 2, okay, 5 divided by 2 is 2, remainder what? 1, right? Then 2 divided by 2 is 1, remainder what? 0, right? 1 again divided by 2, of course, it will be the 0, remainder 1, right? So after you take note of the reminders here, the MSB, there's something indicated here as MSB and LSB. MSB stands for the most significant bit. LSB stands for least significant bits. So how do you go from here? You read now the remainders upwards, right? So you read upwards. Now you say 101011, 101011, and that is the binary number. So you simply divide, take the number, whichever number you are given, go dividing by 2 until there's no more remainder, right? Then the remainder that you are writing here, read them upwards, and that will be the equivalent binary number from decimal to binary. This you have to do practice. Kindly make sure, just take any number, take like 50. Try converting 50 to binary simply by division. Take a bigger number like 120, let's say 127. So you go through the same method, divide by 2 until there's no more remainder. So, and make sure you can also convert this to this or this to this, to and fro. Those numbers should be equal. So that's one technique used all over. Now let's take the decimals here. So how do we convert the decimals? So to convert decimal fractions to binary, there is a repeated multiplication by 2. Here there was successive division. So that's the difference. Here we are dividing, here we are multiplying by 2, right? So sometimes some decimals, of course, are recurring. So in case of that, so you go up to the point where you feel that I want maybe, let's say, 3 decimal numbers or 4 or 5 or whichever number. Remember, some recurring decimals you never add. So you can go multiplying until Jesus comes back or Muhammad or whoever. Then what we do, we have a number here, 0.3125 to base 10, which is a decimal number. We want to convert to what? To binary. How do we do that? Take this number here, multiply by 2, right? So the moment you multiply by 2, so we are supposed to multiply by 2 until the fractional part here. How do you know until when you stop multiplying? Until you get the desired number of decimal places. So the carries here you're seeing produce the answer, right? So you take 0.3125 times 2, that is what? 0.625. You take now 0.625 times 2, it is 1.25. You take this 1.25, actually you take the 0 point, this number at the head, 0.25 times 2, you get 0.5. You take 0.5 times 2, you get 1, right? Up to the desired point. Again, if you take 0.00 times 2, that would be 0. So that marks the head. So you take these bits just before the decimal point. But these again, you read them downwards, right? Remember here we are doing upwards, here read them downwards. So this number becomes now the equivalent of what? A decimal number system, binary number system. And that's how simply we change or convert decimals. So how do we do that? This one, we divide by 2. You successfully divide by 2 until no more remainder. Here, you successfully multiply by 2 until your desired number of decimal places. Or until, like in this case, if you had taken now here, that would be 0.00 now times 2. Of course, any number times 2 multiplied by 0 is equals to 0. So that has no effect here. So that's how we convert decimal to what? To binary. Let's move to the other conversion. I don't know which example this one is. This is a decimal to binary. So this is another example. 125. You go divided by 2 until there's no more remainder. So the remainders here, you read them upwards, right? So this is just what I've explained. So any number, even if it's 10,000 or 10, whichever number you want, 1022, you continuously divide by 2, the round division method, until there's no more remainder. So then these remainders you're writing here, you read them upwards, and that will be the equivalent of that number to binary. So kind of make sure you first of all practice, if it is your first time, practice with what is here or what is in the notes, right? So the moment you practice, it's very simple. Now, that was decimal to binary. So we have converted, already seen how we convert decimal to binary simply by dividing by 2 all through. Now let's go to octal. And again, I want you to see that there's a common thread again for converting to binary. So let's see octal to this one using an example. So to convert each octal digit to 3-bit equivalent binary representation. Now let's see, we have a number here, 705 to base 8, which is octal. We want to convert on that one to base 2 or binary number. So what are you supposed to do? You're supposed to split the number that you have, then like we have done here, 705, then you take the equivalent 3 bits of this number, right? So through the same division that you have seen, as long as there are 3 bits, where are we getting 3? Remember, we said the octal, this is 2 to power 3. 2 to power 3 is equivalent to 8. 8 here is our octal number here. So the 3 bits, they are coming from where? So these are the bits we are talking of. So simply take that number, convert it, then arrange it in what? 3 bits. So convert 5, first of all, to binary through the same method you have seen before, as long as it is 3 bits. If it is 0, make sure it is 3 bits. So usiandike 0 moja hapa. The concern is, or the trick here is that they must all be 3 bits each. So you take the other number, should be 3 bits each, right? So you take the 3 and come and write them here, and simply that is how we convert from octal to binary, right? Let's see the final one. That was octal. Let's go to hexadecimal. So the hexadecimal number system, we have seen from this one to this one, octal to this, then hexadecimal to binary. Now for hexadecimal to binary, instead of now representing the 3 bits like you have said, remember we said that octal we represent in 3 bits. And you have seen where the 3 bits are coming from. The 4 bits, then where are the 4 coming from? Remember here, 2 to power 4 is equals to what? 16, right? So the 4 bits are coming from here. So how do we do that? Let's have an example. Kebi, you're saying that you can't hear. I don't know whether it's only you. Can the rest of you hear? Maybe you can confirm.
Yeah, tunasikia.
So I hope those who are saying they can't hear, probably you check the network on your head or something. Now, this is from now hexadecimal to binary. So remember we are dividing now to 4 bits. So where are the 4 bits coming from? We have said that 2 to power 4 here is equivalent to 16. So the 4 bits are coming from here. So take each individual number, like they have been spread here, then convert each number to binary. After you convert each number to binary, make sure your answer must be 4 bits, right? So even if, of course, 1 doesn't change. 1 in binary is 1, 1 in hex is 1, 1 in octal is 1. But what you're saying, make sure your answer, the preceding zeros don't have any effect, but make sure you have 4 bits each, right? 0 to any other number system is 0, but as long as your answer should be in 4 bits. Then A, again to 4 bits, F to 4 bits. So remember, A is what? This is 10. F is 15. So convert each to binary, then each binary, make sure they have how many bits? 4. If they do not reach 4 bits, you add zeros, preceding zeros. Already you're saying you can't hear. I don't exactly know how many people can't hear. I don't know how many are hearing. So if everybody cannot hear, then it is my end. If it's only you who can't hear, it's likely to be your network on your end. I want to assume that. So probably the rest can just maybe confirm or something. You can type in the public chat or unmute yourself and say something.
I can hear you, sir.
Well, oh, that's who? What's your name?
I'm Sarah. I'm Sarah, sir.
Sarah can hear me. So thereby you're saying that I went off at Octal. So this could not be my conclusion. If actually, at least I can see some are saying that I'm clear, then those who can't hear, the only assumption I can make is the network on your edge. Let me, we were explaining this. This is hex because it is to be 16 hexadecimal number to binary. How do we convert? Create the 4 individual numbers or digits. We have 1, 0, A, then F. Then convert each number to binary. We have looked at how we convert numbers to binary, right? So simply, if you want to convert any number to binary, you just go dividing by 2, by 2, by 2, and take the remainder. So 1 divided by 2 is what? It's 1, remainder 0. So 1 and remainder 0, then you add the preceding zeros. So as long as your answer, especially when you're converting from hexadecimal to binary, you write it in 4 bits, right? So even if itakuja 0 hapa, add the preceding zeros, and that's why you're seeing that we have all these zeros added. If it's 4 bits, well and good. Then take all these numbers and combine them, and they eventually become the conversion from a hexadecimal number system to a binary number system. So make sure you do practice. You can use the practice that I may share this presentation, or
Excuse
use
me,
the
sir.
example. Yes.
And how come that A is 10 and the F is 15?
Very good question. So Sarah is asking, how comes the A is 10 and F is 15? So probably, who can remember why we said why A is 10 and F is 15?
I think because simply from 10 we represent it with A, then 11 is B, then 12 is C, that way.
Yeah, very correct. It is because, remember, the hexadecimal number system starts from 0 to 9. Instead of now moving from 9 to 10, we don't go to 10, we go to what? A, then go to B, C, D, then E, up to maximum F, right? Now, because we're going to go to 10, so this simply means that A represents 10, B represents 11, C represents 12, D here 13, E 14, and F 15. So that is where 10 and 15 are coming from. I hope it's clear, Sarah.
Yes, sir.
Okay, much welcome. Though, make sure you do some practice. Don't be comfortable with just one of them. Take several, convert, and the moment you understand, it becomes very easy and very simple. Now, let's move next. I think we are meeting it on the now one. We have now converted all our numbers, the 3, to binary. So decimal to binary, this to this, this to this. So I think we are now to our second last, how we convert now to octal. So decimal to octal, binary to this, and eventually hexadecimal to what? To octal. So we are just simply moving around, converting one number to the next, right? And the moment you note the thread in each, it's just something uniform. You don't have to go cramming, it's easier. So just take the thread. If you're converting all the numbers to binary, what is the common in the conversion? We are converting to whichever number system. There is something common in each, right? So let's see how we move from decimal to octal. There's an example here. So decimal to octal, we divide by 8, right? And keep track of the remainder. So just like you are dividing by 2 in the binary, here we are dividing by 8 because we are moving to octal. So each number you are given, so we are moving from base 10, which is a decimal, to base 8, which is octal. You simply divide by 8. So 234 divided by 8, that is what? A certain number. I mean, there is a 234. If you divide 234, you divide by 8, that should be 29. Remainder, there's something remainder there. So our concern is the tracking the remainder, right? So we track the remainder, that's our concern. 154 divided by 8, a certain number, remainder something. 19, let's take the simple one here. 19 divided by 8, of course, 19 divided by 8, that is 2. Because 8 times 2 is 16, remainder what? 3, right? So 2 divided by 8, that is, of course, 0, but remainder now the 2. So you read the number upwards. So the simple here, you just require to divide each number by 8. This one must be, I don't know whether this should be 1234 or something, but you can always take any other number. So be it 1234, or maybe you can start with a simple number like 24 or 25, and then convert, but keep track of the remainder. These numbers here are the remainders. Again, read the remainder from top to bottom or upwards. So that's simply how we convert to that. Let's go to now decimal to hexadecimal.
Excuse.
Yes.
Okay. Suppose you take the decimal number, then you convert it to binary, then to octal. Will you get the same answer?
You still get the same answer. You still get the same. So whichever, if you want to convert to binary, then back to the other number system. Actually, just play around without the number system. But sometimes I usually see some people prefer taking this number, converting it to binary, then back to decimal. Whichever method, you get the same answer. Actually, you can just be confirming. If by dividing by 8 you don't get the same number, you can confirm whether you convert to binary, then back to the decimal number system. So let's take the decimal to what? To hexadecimal. So a base 10, you simply divide by 16. To octal, you divided by 8, right? It is as simple as there's a thread. You're going to note that there's a thread. I'd like you to summarize the thread by yourself. So here we have another decimal number. We want to convert to a hexadecimal number system. So you take 1234, divide by 16, then you write the remainder here, right? This number divide by 16, write the remainder here. So our concern in all this, we are tracking the remainder. And remember, in hexadecimal number system, like here you have a remainder of 13. You don't write 13. So you simply go and write from A, then B, C, D, whichever up to F. So if you get a remainder of 15, you don't write 15, you write what? F. In this case, you have a remainder of 13. This is 10, 11, 12, 13. So the D is, so the remainder, if the remainder is anything between 10 and 15, you don't write this value, you now come and pick this on this side here. And that's why you're seeing that it is 4, 13, 2, but you don't write 4, 13, 2. We write 4D, then 2. So simply divide by 16, keep track of the remainder. So as simple as that. So make sure you practice, it will be easier for you. So I think this should be the very last ones. Let me see how very few slides remaining. from binary to octal, actually it is the last bit. So let's go to the last batch here from binary to octal. So you have a binary number, you want to convert it to octal. So how do you do it? So group the bits in threes, starting on the right, convert each to digits. So we are doing the reverse of what we did, octal to binary, right? And this one you have to follow. You may get confused, maybe I'm explaining too fast or I'm going maybe, but you need to take your time and check them. So we want to convert a binary number to octal. So simply what you do, you take the number that you are given, split it into bits of 3, right? So remember 1 is the same as 0, 0 here. Then convert each to what? Convert each binary number to an equivalent octal. So it is as simple as that. So you split the number you're given, then convert each bits to octal. The case of hexadecimals, you convert into 16, you split the bits into 4s. So that's the thread I'm asking you to take note of. Then binary to hexadecimal, just as I explained, group the bits into 4s, then convert each 4 bits to the equivalent hexadecimal number system. So here we group into 4s, then convert to hexadecimal systems. So you take a number like this one, you want to convert to hexadecimal, you split this one into 4s, 1, 2, 3, 4. This one, 1, 0 there is equivalent to 0, 0, though the preceding zeros don't make any effect. So convert each number to a hexadecimal number system. Alternatively, you can convert this one to decimal number, then decimal to hexadecimal, just like somebody suggested. And you're supposed to be getting this result. So the moment you got the notes, take note of the thread. It will be so easy. It will be easier to follow the thread. The octal to hexadecimal. So use binary as intermediary. So this has already been suggested. Convert first 4 to binary, then binary to hex. Right? Remember, some numbers you cannot just convert direct. So how do you do? You do as somebody suggested. You convert to one number system, then to the other. So again, this is to base 8 to 16. We first of all convert from base 16 to binary. Then binary to, now you convert to the hex. So that's what you're saying, the intermediary. I wanted us to take at most 1 hour, is almost over. So I'll be finishing in the very few seconds or minutes. So again, you want to convert hexa to octal. So you can go through binary, then convert to, that's what we are saying. Allow me to pick a call. I don't know who is calling. So this is what you're saying. If you want to convert from hex to octal, you go through the binary. If you want to convert octal to hex, you first of all take the octal, convert to binary, then binary to hexadecimal. That's how you are saying that you have to go through some sort of an intermediary. Then the last one here, which is hexa to octal, that's what I've explained. You first of all take hexa to binary, then from binary to octal. That's the easiest way. So how do we do it? There is an example here. So we have a hexadecimal number system. So convert each must be to 4 bits first to what? To binary, right? And now because we're moving to octal, the line here you're seeing is simply that the bits has been split into 3 because we are going to octal number system. So you take 1 in hex must be 4 digits, so 0001, 3 of them. So convert to binary each number. Remember F is 15 here, and don't forget also to change C. After that, you split again to 3 bits. 3 bits because you're going to octal. Then convert each 3. 100 to octal, 001 to octal, 100 to octal, and in that order until you get this. So make sure you go through the notes, do some practice. The moment you get hold of the trade, it will be so easier for you, right? It will be so easier. So here there is a small exercise. We are converting from decimal to binary, octal, to whichever. So you're supposed to take 33, convert to binary, to octal, to hexadecimal. Take the binary number here to decimal, to octal, and to hexadecimal. Then take the octal number, this 8, convert to binary and decimal and to hexadecimal. Take this one, hexadecimal number, convert to the rest. And so I would want you to also do some practice, try convert each number to a different number system. And then that way, the moment you do practice of 1 or 2, you'll be able to understand that and it becomes very simple for you. So in case you have any challenges, make sure you always, you can post in the group, you can ask your members, you can ask me, or you can Google, or you can use, and you don't use a calculator this time around. We have online systems where you just put the number then it converts for you. Use the online or calculator only when maybe you want to confirm your answer. That will be okay. But don't just maybe put it, you'll not know, because the objective is understanding how we do it. So understand, go online, try just confirming your answer from there.